Okay, in this sub-element, we talk about antennas, vertical and horizontal, the concept of gain, common portable and mobile antennas, and the relationship between antenna length and frequency. And first question is, what is a beam antenna? It's an antenna that concentrates signals in one direction. And one way you can think about that is like how a flashlight makes a beam. If you just have the little naked bulb there, the light's going in all directions, but you put a reflector in your flashlight to point the energy in one particular direction that you want to use it. So this could represent your bulb, and here's your reflector, and then you could have lenses or other things out in front of the bulb, again, to focus the beam the way you want it to. So in a beam antenna, we have an antenna that concentrates signals in one direction, just like a flashlight concentrates light into a beam. Let me back up because I didn't name that antenna for you. This antenna is called a Yagi. It's called a Yagi, and it's a particular design. There are other beam antenna designs. This is a cubical quad, which is similar to a Yagi in performance. It has a driven element where you apply the energy to it, and it has reflector, which is slightly larger than the driven element. It has one or more directors, which are slightly smaller than the driven element. This is a corner reflector, and here you just have the driven element, and then you have a reflective surface out here behind it to direct the energy in the direction you want it to go. This is called a log periodic, and it's also directional. It doesn't have as much gain. It doesn't focus energy as much as the Yagi does, but it has the advantage of being a very wide band antenna, so it covers a wide range of frequencies. And then the parabolic antenna is like the lens in the flashlight, isn't it? So up here is the driven element, which focuses, which illuminates the reflector, just like the bulb in the flashlight illuminates the reflector, and then that sends out the beam. Which of the following is true regarding vertical antennas? With a vertical antenna, the electrical field of the antenna is perpendicular to the earth. So here we see a vertical antenna. Here's the earth. Here's the vertical antenna element, and this will radiate a vertically polarized signal. Which of the following describes a simple dipole mounted so the conductor is parallel to the Earth's surface? Di means two, doesn't it? Pole, we have two poles here. We have this length of wire here, this length of wire here. Total length is 1/2 wavelength, which is the basic antenna wavelength. And here it is mounted so the conductor is parallel to the Earth's surface, and it's a horizontally polarized antenna. So here we're perpendicular to the Earth's surface with a vertically polarized antenna. Here we're parallel with a horizontally polarized antenna. What's a disadvantage of the rubber duck antenna supplied with most handheld radio transceivers? The rubber duck is that little rubber antenna that comes with your handheld. It's handy, it's pretty rugged. They mostly don't get broken up too much in the first couple of years. But it does not transmit or receive as effectively as a full-sized antenna. Remember I said the half-wave antenna is the basic antenna length, and the half-wave antenna for a 2-meter transceiver would be over 1 meter long, so not nearly as handy to stick in your pocket and walk around with. How would you change a dipole antenna to make it resonant on a higher frequency? It's important for an antenna to be resonant because that's when it radiates the energy the best. And we know that if we go higher in frequency, we go to a shorter wavelength, higher frequency, shorter wavelength. So we would shorten the antenna to match the wavelength. What types of antennas are the quad, the Yagi, and the dish? They are directional antennas, and we saw pictures of those earlier. What is a good reason not to use a rubber duck antenna inside your car? The signals can be significantly weaker than when it's outside of the vehicle. You have the metal body of the car, which blocks signals. Also, some of the tint material on some cars. Especially the factory supplied tint on the upper portion of the windows can be metallic, and that can cause your signal strength to be weaker also. What's the approximate length in inches of a quarter wave vertical antenna for 146 megahertz? Okay, we have a magic number here of 234, which is the constant that we use to figure a quarter wave antenna. We take 234, divide it by the frequency in megahertz. Okay, so here we've done that, 234 divided by 146 megahertz, and we get an answer of 1.603 feet for our antenna length. Okay, but it asks us for it in inches. So to get it in inches, we have to take our 1.603 multiplied by 12, and we get an antenna length of 19.23 inches. So you can remember that, or you can just remember that for a quarter wave antenna for 2 meters, it's about 19 inches. Excuse me for a second. What's the approximate length in inches of a 6-meter half wavelength wire dipole antenna? Okay, now we're at 6 meters. The frequency is 50 megahertz. Remember, I asked you to learn what the frequency limits of those various bands were, and here's where you need it. Now, if the quarter wave antenna had a constant of 234, you could probably guess that the half wave antenna has a constant of 468. Okay, so we're going to take 468. We're going to divide it by the frequency in megahertz, and that's going to give us 468 divided by 50 is 9.36 feet. Okay, the question asks us in inches, so we're going to take 9.36, multiply by 12, and we get 112.32 inches, and this is the answer that is offered to you on the test, 112. Okay, any questions on those?
No.
No questions. Okay. Okay, in which direction is the radiation strongest from a half-wave dipole antenna in free space? Here's our antenna right here, right in the middle of that donut-looking thing there. And this has been cut away there so you can see the antenna. But your radiation is strongest broadside to the antenna. So here you have a radiating antenna. It will be strongest broadside to the antenna and less strong off the ends of the antenna. Okay, broadside of the antenna is where the strongest radiation is. What is meant by the gain of an antenna? The gain is the increase in signal strength in a specified direction when compared to a reference antenna. Now, we just took a look at that. Let me back up to it here. We just took a look at this half-wave antenna. Now, let's suppose that the station I want to talk to is out here. So instead of sending this energy all out around the antenna equally, I'm going to want to focus some of that energy out this way to where I want the stronger signal. And focusing that energy, cutting off this energy back here, pushing it out this way is what creates the gain. Okay? So let's take a look at some patterns here. One way to do that is to use an antenna like a Yagi. And if we look at the Yagi, we can see that it has very little signal off the back, a lot of signal off the front. So we've taken that energy from the back, pushed it out the front of the antenna. Okay. Another way to do it, like on a mobile antenna, instead of having a lot of signal going up here where there aren't any stations that we want to talk to, we can design an antenna that will pull that down toward the horizon so we get gain here, down where we can use it, instead of up here where we can't use it. Okay, so the gain of an antenna, the gain is created by increasing the signal strength in a specified direction when compared to a reference antenna. And the reference antenna would be one that radiates in all directions.